So today we are going to talk about two concepts, phylogenetics and systematics. I will remind you of what the tree of life looks like. Then I will motivate the lecture basically by recalling the history of systematics. And then I will go into basically what phylogenetic concepts are and how to build a phylogenetic tree. So here is the tree of life. And basically it shows you that about 3.5 billion years ago, there were three large clades that had developed. Take a moment and look at this picture. This picture provides the relationships, and these relationships still changing. What I'm going to sketch today is how the phylogenetic biologists got it. Well, it actually has taken a very long time for phylogenetics to set on clear logic and clear methods. They were implemented until about 1965 to 1970 by Hanisch. And they ensured a huge controversy that lasted for about 20 years. Hanisch proposed three questions. First, what is a phylogenetic relationship? Second, how is it established? And third, how is knowledge of it expressed so that misunderstandings are excluded? And his answers were precise. Phylogenetic relationship meant geological relationship, expressed as a series of nested sister group relationships where two taxa are more closely related to each other than they are to a third. These sister group relationships are established by spatial similarity. The expression of these relationships is presented in a branching diagram summarizing the sister group relationships termed a cladogram. Although Hanisch had a view of species very close to that of Mayer and the evolutionary taxonomists, the answers to Hanisch's three questions set his framework apart. In the first place, he defined phylogenetic relationships strictly in terms of recency of common ancestry. His emphasis was entirely on the clade as opposed to the grade. This was a definition that removed the uncertainties that exist in nearly all classification schemes. Today we struggle with different criteria to distinguish between competing and disagreeing evidence. But in contemporary systematics, several methods are used to make these judgments based on first, parsimony, second, likelihood, and Bayesian techniques. Although they differ in their criteria, they all agree that groups must be monophyletic in a Hanischian sense, that classifications must match geological exactly, and that evidence must rely on spatial similarity. All systematics today, whether they like or not, are Hanischian cladists. Now we are going to introduce the fundamental concepts of systematics. First, characters. Characters are the basis of systematic analysis. We mean that characters are not unorganized observations, but ones that convey notions of relevance, comparability, and correspondence. This is important to keep this in mind as we attempt to test the hypothesis of character evolution and relationship in as rigorous a manner as possible. In general, we would like to include as broad and large a collection of characters as possible. This may include molecular sequence, developmental expression, anatomical information, and behavioral observations. Systematics being classifiers typically divide characters into classes: morphological, molecular, behavior, developmental, and so on and so forth. Although these classes can have descriptive meaning, they do not require that their variation be valued differently. The argument over whether to evaluate all characters simultaneously or separately has focused on two very different ideas of the determination of the best phylogenetic hypothesis. The concept behind partitions analysis is one of the robustness as opposite to one of the optimality and quantity. This will be discussed later in more detail. Traditionally, there are characters and character states. Characters, which represent comparable features among organisms, and character states, which are the set of variations in aspect or expression of a character. This distinction between the two concepts has always been fluid and in dynamic homology, largely meaningless. Let's look at the next concept, taxa. Taxa are collections of organisms. A taxon must consist of at least two creatures. An OTU is any object that occurs at the tips of the tree. OTUs might be parts of individual creatures, individual organisms, species, collections of species, or higher taxa. These are normally the inputs to systematic analysis. HTUs, on the other hand, are not observable. It's not a real thing. They are abstraction created at the nodes of trees. They are hypothetical since they cannot be observed in nature and only exist as interpretive objects on a tree. At times, these HTUs can stand in or be mistaken for ancestral taxa. The next concept is tree. Trees are the central objects of systematic analysis. Taxa are ordered, characters explained, and hypotheses tested in trees. Since systematics informs and draws on other areas of science, there is a diversity of terminology for trees and their components. This section will lay out the basic definition and description that are commonly used. When trees are rooted, there are three types of groups can be delimited. The first, monophyletic, second, paraphyletic, and last, holophyletic. So far, we have learned the concepts of characters, taxa, and the trees. And the next time, we are going to talk about species concepts. You can preview this part online and let me know the most difficult section for you. Thank you. That's all.